Today we're going to be starting chapter 14. And in chapter 14, we're going to be talking about rational functions. What's up?
Can I take my test tomorrow morning during study hall?
I have no problem with that.
Okay.
That's fine. Yeah, that's okay. Should be waiting for you in the study hall room.
Okay, perfect.
Yep. You know it's a mass day though, right?
Yeah, so it's, what time do I have to do?
I mean, it's the first hour starts.
We're done with the
Still,
second hour. We're done with the first hour next tomorrow.
Oh, it's not actually 8:50.
What time is that?
You have to be. Yeah, it'll be fine.
okay.
Yeah.
Yeah, I'm just reminding you.
Yeah.
That's all.
Thank you. I forgot.
It's okay. All right. So we want to start by defining what we mean by a rational function, because maybe you didn't get this far in your Algebra 2 class in the past. So let's make sure we are careful about what we're doing here today. So we say that r of x is a rational function if it can be written as some p of x over q of x, where p and q are polynomials and q is non-zero. Okay, so we know what polynomials are, right? That's what we just got done doing. So basically what a rational function is a new type of function that's being built from polynomial pieces. Or just like one polynomial divided by another polynomial. That's my new function. Everybody's okay with that? Okay. In this first section, we're going to be worried about finding what I'm going to call key features for our rational function. So we're going to be talking about finding the domain, finding discontinuities, x-intercepts, y-intercepts, horizontal or slant asymptotes, and then end behaviors. So today we're going to spend some time talking about how to find each of these, and then depending on how long that kind of takes us, we'll talk about how we can take those attributes then and put them together and build a graph, or a reasonable sketch of a graph out of those. So that's kind of the goal at the end, is going to be like, how can I take these things and turn it in, if I collect these all together, can I turn these into a picture? But that's what we're going to be doing today, okay? So we're going to look at these 6 different attributes and talk about how to find them. And if time permits, we'll start talking about how we can put them together and making a graph or making a sketch of a graph. If not, we'll get that next time. Okay? We did not get that far during second period, so. Okay. So the first thing we'll talk about is the domain. So to find the domain, we're going to set the unreduced denominator equal to 0 and solve. The solutions to that equation are the values of x that are not in the domain. So solving that equation is going to give us the holes in our domain. So we'll have, our domain will be everything except for those values, and then we'll write our domain from that. So let's look at a couple of examples. So my first example is going to be y equals x plus 4 over 2x minus 1. So to find the domain, I'm just going to take the denominator and set it equal to 0. That's just a linear equation, so that's really easy to solve. Just add 1 to both sides, and then divide by 2, and the solution there is 1/2. So that's the only value of x that's not in my domain. So my domain needs to be everything except x equals 1/2. Now, we're not going to write our domain in words. We're going to write it using an interval notation. So we're going to need 2 intervals to describe everything except for 1/2. We're going to need everything before 1/2 and then everything after 1/2. So everything before 1/2 starts at negative infinity and goes up to 1/2. And I'm going to use a parenthesis there because the parenthesis in interval notation indicates that 1/2 is not included in that set of numbers. So that's everything up to 1/2. And then we'll do everything after 1/2. So we'll start at 1/2, but not including it. That's why I'll use the parenthesis. And go to positive 1, or positive infinity. So that's everything before 1/2 and everything after 1/2, but not including 1/2, which is what we want. So that would be like what our answer looks like. Everybody feel okay there? Let's do one more, and then we'll move on to the next thing. So my next example is y equals 3 minus x over x cubed minus 4x. Just like before, I'm going to take the denominator and set it equal to 0. Now I notice that this is not a linear equation here. This is a polynomial equation, right? How do I solve a polynomial equation? My hope is that I'll just be able to use my factoring tree from last chapter. Everybody okay with that idea? Again, when solving for a polynomial, this is the first stop. Hopefully I don't have to do synthetic division. I almost assure you in a chapter like this that would not be part of the problem. So it should be something that's factorable. So let's go back to where we were. So when I looked at that factoring tree, the first thing I need to do is look for a greatest common factor. Is there a greatest common factor between x cubed and 4x? X. So if I factor an x out front, I'll have x squared minus 4 left. Everybody good there? If I look at the x squared minus 4, that has two terms. If I go down the two-term branch of my factoring tree, the first thing I want to check for is a difference of two squares. Is x squared minus 4 a difference of two squares? It is. How does that factor then?
X plus 2 and x plus 2.
Great. Does it matter if you say x minus 2x plus 2? No. Whatever order you want is fine. No big deal. Everybody happy there? Now it's factored completely because each factor is linear. They're all degree 1 factors, so I know that I am done. So I can then just set each of these factors equal to 0 and solve. Is everybody okay with how we did that? Okay. So now let's write our domain. So I know my domain is everything except the numbers 0, -2, and +2. Everything has to start at -infinity. Which of these three values is the first whole in my domain? -2. Why -2? It's the smallest number. It's the first one you'd encounter starting at -infinity. Okay, and then we're going to go from -2. What's the next whole? 0. So -2 to 0. And then we'll go from 0 to the next whole, which is 2. And then we'll go from 2 to everything else because we're out of holes now. What do you guys think on that? Really no more complicated than previous one, other than you have like 4 intervals here instead of 2, but like, who cares? It doesn't make it really any harder. It just makes it longer. Is everybody okay there? All right. Any questions on domains? That should feel pretty okay. So now we'll talk about discontinuities. So there are 3 types of discontinuities. This is true for all functions. So there are infinite discontinuities. We call those things probably vertical asymptotes, is what you've called them in the past. There's holes. We call those removable discontinuities. And then there's jumps, or just a jump discontinuity. So I'm just going to kind of sketch a picture here off to the side to kind of show you what we're talking about. Jump discontinuity. So here's a little picture that just kind of illustrates these 3 different types of discontinuities. So So our infinite discontinuity just is a vertical asymptote. We know what that looks like, I hope, right? It's a line the graph can approach but cannot cross. The next one is a hole. So that's just like 1 point missing out of our graph somewhere. That's just like a missing point. And then the jump is where the graph stops in one location and picks up and starts in a new location. The good news is our rational functions can only have vertical asymptotes or holes. They cannot have jump discontinuities. Does everybody feel okay as to like what these things look like? Okay. Then the next thing we're going to do is we're going to talk about how to find them algebraically. Yes, sir. Sure. Okay, so to find our vertical asymptotes, we're going to set the reduced denominator equal to 0 and solve. And the solutions to those x equals, are going to be the equations for the vertical lines representing our vertical asymptotes. Remember, the equation for a vertical line starts x equals as opposed to y equals. So to find the removable discontinuities, we're going to set any factors completely reduced from the denominator equal to 0 and solve. These solutions give the x-coordinate to the removable discontinuities. To find the corresponding y-coordinates, we're going to plug those solutions back into the reduced function and just simplify. So remember, the hole is a point. It's an xy. It's the location that's missing, the point that's missing from our graph. So it's going to be an x and a y. So notice that in both of these, we're worried about the reduced denominator, right? So let's talk about what that means, and we'll do a bunch of examples here while we're doing that. Actually, I'm going to do this. I'm just going to move this example to the bottom. Actually, the easier way to do that would just be just do that. Okay. Yes. Oh, yeah, I guess I lost that 4 somewhere, huh? Okay. So, first thing we need to talk about is how to reduce one of these rational functions, right? So, the first step in reducing is to factor. So if I go to look at this, x plus 2, well, that's already linear, right? There's really no factoring to be done because there's no greatest common factor. So there's nothing to do on the top. The denominator, though, is quadratic. Since the leading coefficient is 1, I can factor this just by finding thank you. The two numbers that multiply to give us 5 and add to give us 6. What are those two numbers going to be? 1 and 5. Everybody's okay with how we factored that? Now, the expectation is going to be that for these simple quadratics, where the leading coefficient is 1, and the product is like a normal multiplication table product, that you can do this like inside of 10 seconds. Okay? Now, my question for you is, to reduce this, can I do something like this? No! You cannot reduce like that. What is wrong with what I've done? Correct. I can only reduce the entire thing or nothing at all. I cannot reduce part of an addition or subtraction problem. Okay? I will tell you this. If you reduce like this on a quiz or a test, there's no partial credit for that problem. That is automatically 0 points. Okay? I'm going to make that clear right now that this type of reducing is not okay. It is 0 points if you reduce this way. Is there any reducing that can be done here? No, because there's nothing. The x plus 2 in the numerator is different than either the parentheses in the denominator, right? So if I can't reduce anything, can I have a removable discontinuity? No, because I need factors completely reduced from the denominator. If I didn't do any reducing, I can't have any of those, so that's just, there's none of those. So my vertical asymptotes are just going to be from the factors in the denominator set equal to 0. So I have two vertical asymptotes for this problem, one at x equals -1 and one at x equals -5. Troy? Sure. Everybody feel okay there? Sure. Should go on to the next one. Okay. Start the same way. Let's factor. So nothing to do with the top. X squared plus 5x plus 6. What multiplies to give us 6 and adds to give us 5? Good. 3 and 2 or 2 and 3, doesn't matter. Now for this one, is there anything that can reduce? Yes. What can reduce? The x plus 2's. When I reduce that, what do I have left? I have 1 over x plus 3. Does everybody feel okay there? So for my removable discontinuity, notice that I did reduce something completely from the denominator. There is no more x plus 2's. So that's what I'm going to set equal to 0 and solve. Everybody's okay there? To find the y coordinate now, I'm going to take that result and plug it into the reduced function. So that just gives me 1. So my removable discontinuity is at the point -2, 1. Does everybody feel okay with what I did there? Now my vertical asymptote is just going to be from the reduced denominator, set equal to 0. So there's my vertical asymptote at x equals -3. So far, so good? Okay, let's move on to the next example. How do we start? Factor, right? Nothing I can do to the numerator, the x plus 2's clearly not factorable. How about x squared plus 4x plus 4? What does that factor to? Very good. Do we see anything that can reduce? X plus 2 can reduce. So 1 copy from the numerator can reduce 1 copy from the denominator. Okay. Do we have a removable discontinuity? No. Because even though I reduced an x plus 2, I still have x plus 2 in the denominator. It was not completely reduced. I just was able to do some reducing. So this is still none, because that factor is still there. So, vertical asymptote time and I just get x equals -2. As a check, if you had missed that, there was still an x plus 2 left over, if the x-coordinate for your hole matches the x-coordinate for your vertical asymptote, you've made a mistake. You found a hole that shouldn't really be there because it was not completely reduced from the denominator. So if you had missed that and counted that as a removable, and then continued on, you would have had the x-coordinates matching for the hole and the vertical asymptote. That can't happen. You've made a mistake. You probably counted a hole that shouldn't be counted. Or you factored wrong. That could have happened too. Okay. The last one here. Again, numerator, nothing to factor there. Can I factor x squared plus 1? No, right? That's not factorable. Why not?
Because it's not a difference of squares.
Yeah, it's not a difference of two squares. It's a sum. The sums aren't factorable. Okay, so if I can't factor this, what does that tell me about a removal discontinuity? Can't have any of those. So I'll just take x squared plus 1 and set it equal to 0 then. Since there's no x term, it's just x squared, I can just solve this directly, right? I'll subtract 1 from both sides and then square root both sides. And what's the square root of -1? Nope. Nope. It's I. That's a non-real answer, right? What is that telling me? If I get a non-real solution, I can't have a vertical asymptote. So this rational function has neither vertical asymptotes nor removal discontinuity, which can happen, right? You can have both, you can have one or the other, you can have neither. Any of those are possible. Do you guys feel okay about this process of how to find these things? Again, like the sub-problems are not difficult. What's difficult is remembering what to do to find each of the things, right? The individual routines are easy. Like remembering what does what is the hard part. But what do you get for the test? A note card, your half sheet. So that hopefully makes life a heck of a lot easier because you're able to keep things straight. Make some notes for yourself. All right. Next thing, we're going to do our x-intercepts or the zeros. They don't happen for rational functions. So we don't have to worry about it in this section. It only happens for piecewise functions, which are beyond the scope of what we're going to study in this class. But they are a thing, so I just thought I'd mention it because there are 3 types. They just can't happen for rational functions, so easy enough. Okay, so to find the x-intercepts, yes, sure. We're going to set the reduced numerator equal to 0 and solve. The solutions are the x-coordinates for those x-intercepts, and the y-coordinate is just always 0 for an x-intercept. Everybody okay with that plan? Okay, so we have 3 examples. The first one, y equals x minus 1 over x plus 2. So the first thing I'd want to do is to check to see if I can reduce this. Is there any reducing to do there? No. So all we'll do is we'll take the numerator and set it equal to 0. That gives us x equals 1, so we have the x-intercept 1, 0. Now I'm going to be very careful when I'm doing this to always write my x-intercepts as points and not write it as x equals 1, because that's also the same way I'm going to write my vertical asymptotes, and I don't want to confuse my x-intercepts with my vertical asymptotes, right? My vertical asymptotes are a vertical line. They're an equation for a line. My x-intercept is a point. I'm going to be very careful to write my x-intercepts always as a point as opposed to like x equals 1, which is not incorrect, but it's really kind of crummy notation in this context because very easy to confuse that with a vertical asymptote. All right. My next one, I'm going to start the same way. I'm going to try to reduce, so I'll start by factoring. The denominator is just linear, so I know that's not going to do anything. That's factored already. How does the numerator factor? X squared plus 3x plus 2. X plus 2 and x plus 1, right? Is there anything that can reduce? No. So we're done. Nothing to reduce. So I have one x-intercept at negative 2, 0. And a second x-intercept at negative 1, 0. So you can have one x-intercept, you can have multiple x-intercepts, right? Let's look at the last one here. Again, we're going to start by trying to reduce, so we'll start by factoring. X squared minus 1, does that factor? Yes, that's 2 terms. It's a difference of 2 squares. What does it factor to? Very good. Do we see anything to reduce? The x plus 1's reduce. Now notice what's left in the numerator. No variable anyway, right? It's just a number. So what's that tell me about x-intercepts? There aren't any. So you can have one x-intercept, you can have multiple x-intercepts, or you can have no x-intercepts. It's fine. Everybody feel pretty good so far? Okay. Next up are going to be y-intercepts. So to find the y-intercept, we're just going to plug 0 into our unreduced function and simplify. The result is going to be the y-coordinate for that y-intercept, and the x-coordinate is just going to be 0. So again, we don't have to worry about reducing to do the y-intercept. I just plug 0 in, and that gives me the y-coordinate for 0, comma, whatever. So when I do this one, I get 0 over 0. Uh-oh, what does that mean? Yeah, it's something different than undefined. It's actually called indeterminate, but whatever. If you said undefined, that's close enough to me, which tells me there is no y-intercept. In this problem, there would actually be a hole there. That's the location of a hole in this graph, but whatever, right? Everybody feel okay? So again, the undefined or indeterminate is when you have a 0 in the denominator. The 0 in the numerator is fine if the denominator is a number other than 0. Like 0 over 2 is just 0. 2 over 0, undefined. Everybody's so far so good? Yes, sir. So again, like, to find these things, it's really simple. Like the little calculations and stuff we have to do, or the little solving problems, is easy. There's just a lot of different things to find, and they all kind of sound like the technique all feels kind of the same. It's easy to get turned around, but that's why we're going slow and being careful and trying to do a bunch of example. So the next thing we're going to do is talk about finding the horizontal asymptote or slant asymptote. And every rational function has one or the other. None of them have both. So to find these horizontal asymptotes or slant asymptotes, we're going to be comparing the degree of the numerator with the degree of the denominator. So if that's the case, there's 3 possibilities. The first is the degree of the numerator is less than the degree of the denominator. And in this case, we have always y equals 0. In case 2, we could have the degrees are equal. In that case, you're going to have, I should probably say these are horizontal asymptotes. So you're going to have a horizontal asymptote. Again, but this time to find it, it's going to be the leading coefficient from the numerator over the leading coefficient from the denominator. So it'll be a number other than 0. Everybody still doing okay? The third case is the hard one, where the degree of the numerator is greater than the degree of the denominator. Here you're going to have a slant asymptote, and it's going to be y equals the quotient of numerator divided by denominator. So you're going to have to do, in case 3, we'll have to do some kind of polynomial division, either synthetic division or long division. And the quotient from that will be our equation for our slant asymptote. Okay, so here again we have 3 examples. So the first thing I want to do is look at the degrees . So for A, 5 over x plus 3, the degree of the numerator is, it's not 1. 0. Why is it 0? Because there's like no x term there. It's x to the 0. Because x to the 0 is just 1, right? So there's like an x, and the degree of the denominator is 1. Since 0 is less than 1, I know we're in case 1. So we have a horizontal asymptote at y equals 0. That was our rule. If the degree of the numerator is less than the degree of the denominator, always horizontal asymptote, always y equals 0. Part B, we have 6x plus 1 over 2 minus 3x. The degree of the numerator is 1. And the degree of the denominator? Not 0. It's also 1, right? There's a 3x down there. Just because we didn't write it first doesn't mean it's not the highest degree term. since 1 equals 1, this is case 2. So we have a horizontal asymptote, and it's going to be leading coefficient of the numerator over leading coefficient of the denominator. So don't forget to take the negative sign with the 3 there, right? That's really a negative 3. So our horizontal asymptote would be at y equals negative 2. So far, so good. The degree for my numerator is 2, and my degree for my denominator is, since 2 is greater than 1, that's going to be case 3. So to do this, I need to do some polynomial division. Should I do long division or synthetic division here? Why can I do synthetic division? Yeah, very good. My denominator is monic. That's what we call that, where the degree is 1 and the leading coefficient is 1. So that's tailor-made for synthetic division, and I'd much prefer to do that than long division if I'm given a choice. Everybody's okay with the setup? Just remember, remainder, constant x. So this is the stuff that I care about. So the quotient is going to be 1x plus 3 I do not give one little thought to that remainder. It does not tell me anything about the asymptotes. I do not care. Everybody's good? The only place I might care is if it was 0, but in which case then all you have is like a line, right? You just have y equals x plus 3 left, and that's just a line with a hole at whatever the thing that would have reduced from the denominator. But that's on you for not catching the reducing. Okay. So far so good? Okay. Last thing to talk about for these key features is end behaviors. So remember from last chapter, polynomials always had 2 end behaviors, right? Rational functions have 2k plus 2 end behaviors, where k is going to be the number of vertical asymptotes. So I'm going to start here by doing an example where we're going to go from looking at a picture of a graph to the end behaviors. And then after that, we'll do an example of just an equation to end behaviors. Everybody's okay with that plan? I think starting at the picture, it's a lot easier to visualize what's going on. Once you've had an idea of what's going on, then we'll take away the picture and do it without that. But you don't have any intuition yet, so the picture I find really helpful. So let's say that this function here that we're going to draw has 3 vertical asymptotes. How many end behaviors are we going to have for 3 vertical asymptotes? You can have 8. 2k plus 2. So 2 times 3 plus 2. That's 8 end behaviors, right? So I'm just going to kind of draw in some arbitrary ones. So let's say that we have this picture. Now we said there were 8 end behaviors for this function. Those 8 end behaviors are going to correspond to the 8 arrows on our graph. I'm going to have one end behavior for each arrow. Is everybody okay with that? So remember, for our end behaviors, we said that we're going to write it like this, right? Each end behavior is going to be written like that, where we just have to fill in those 2 blanks. This blank is going to be like our x, and this blank will be like our y. So the way I'm going to think about this then, to figure out what x and y I'm going to be filling in, is I'm going to look at the end of the arrow, and I'm going to think about that as like a point. So because that arrow is pointing to the left, the x value is like -infinity. And because it's flat, like hugging that line, y equals 0, its y value is like 0. So my first end behavior then will be the limit as x approaches -infinity of f of x equals 0. If I look at 2, that arrow is right at x equals -3, but it's pointing down. So the x-coordinate's like -3, and the y-coordinate is like -infinity. So you guys kind of see that? So here we'll write the limit as x approaches -3 of f of x equals -infinity. If I look at 3, the x-coordinate here is also at like -3, but the arrow's pointing up, so that means the y should be +infinity. But now I've done something that we shouldn't like. What have I just done that looks wrong to you guys? So I've basically drawn a function that has the same x-coordinate, -3, but two different y-coordinates, -infinity and positive infinity. Can a function have the same x but two different y's? No, right? That can't happen. So we need to do a little designation here to make it clear that that first limit that we've written is -3, but it's talking about the left-hand side of -3. And the other one, the third limit that we've written, is talking about like the right-hand side of -3. You guys kind of see that? So the way we're going to indicate that is with a superscript on the -3. So we're going to put a negative sign in the superscript to represent the left side of -3, and a plus sign in the superscript to represent the right side of -3. Is everybody okay with that? And that's going to happen for every vertical asymptote. Is I'm going to have a left limit and a right limit, because every vertical asymptote is going to be at the same x value. So if I look at my end behaviors for 4 and 5, I'm going to have the same thing going on here. So I have the limit as x approaches -1 from the left. And then for 5, I'll have the limit as x approaches -1 from the right. You guys kind of see that, what I'm doing? So again, if I write my 2 now, for 4 and 5, they're both -1, but they're both pointing down. So these should both equal -infinity, right? Why don't you guys try to write 6 and 7 on your own here? We'll take a minute. For those of you following along, try to write 6 and 7 on your own. I'll write the answers here and start writing my answer in 30 seconds or so, just to give you a little head start. But it's nice to kind of try it on your own and see how you do. So I got my answers written up there. Take a moment if you've had a chance to write yours in and check them against mine. See, how did you do? Thumbs up, thumbs down, thumbs sideways. See some thumbs up and a lot of non-responders, which is fine. I'm happy for some thumbs up though. And then our last one is 8. Notice on 8, our arrow is pointing to the right, so that's positive infinity, and it's flat against the line y equals 2, so the y coordinate would be 2 there. Does everybody feel reasonably okay with how we're writing these end behaviors? This was kind of shaky on the last test, why I wanted to give a really in-depth and time-consuming example here to really hammer the notation again. I want to point out to you that these two chunks, those two specific end behaviors, are the same for all functions, right? They all have an end behavior at -infinity, and as x approaches -infinity and x approaches positive infinity. Those are the +2 here that are always there regardless of whether you have asymptotes or not. And then all of these guys in here are the result of having the asymptotes. So far, so good. Let's look at an example where we use the equation. Where we just have the function, the equation. Now, I'm going to do this problem as if I don't have a graphing calculator to just type this in and look at the picture and do it the same way we did the previous one, which is fine. You can still do things that way. But I want to show you also how you would do it without having to look at the graph. Sure. So the two things that I need before I start this problem is I need my vertical asymptotes and I need my horizontal or slant asymptotes. Everybody's okay with that? So I notice that this doesn't reduce at all. So to find the vertical asymptotes, I'll just take the denominator, set it equal to 0. I'll get x equals 2. And I know that the degree of the numerator is 1 and the degree of the denominator is 1. So I'm going to have case 2. So y equals the leading coefficient of the numerator, which is 1, over the leading coefficient of the denominator, which is 1. Everybody's okay there. So right away, I can write, I know I have 4 end behaviors, right? Because I have 1 vertical asymptote. So 2 times 1, and then plus 2. And I know right away that the end behaviors I'm going to have are going to look like this. You guys feel okay there? So again, my vertical asymptote is giving me these 2. I guess I'll do it in color coding. Oops. So vertical asymptote's giving me these 2. And then these 2 are standard for all functions, right? Now the good news is the yellow end behaviors are just going to be the same as that horizontal asymptote. If it was a slant asymptote, they would be positive or negative infinity, depending on if the slope was positive or negative on the slant asymptote. So all I need to do now is figure out whether these are going to be positive infinity or negative infinity. Because those ones at the vertical asymptotes will always be positive infinity or negative infinity. So what I'm going to do is I'm going to check the left side first. So I'm going to look at values that are getting closer to 2, but from the left-hand side of the number line. And then I'm going to look at the right side. I'm going to be looking at numbers that are getting closer to 2. from the right side of the number line. Everybody's okay with that? To find those, I'm just going to plug them in. And you could use your calculator to do this. I'm just opting not to. So what do we notice that's happening here? Is that it's going down, right? The closer we're getting to -2, the smaller my number is getting. So that's telling me that I should have negative infinity for that one. We'll do the same thing over here. So that tells me we're going up. So I should have positive infinity for that one. Yes, Kirsten.
Could you draw a graph to this?
Yes, if you wanted to, you could just type it into your calculator and hit the graph button to look at it. Totally fine. I'm just kind of talking through how you would do it without having to generate a graph. Because a long time ago, this is how you did it without having, because we didn't have graphing calculators. And generating a graph on your own, like you didn't know whether the graph, whether the end behavior should point up or down without doing exactly what we're doing right now. So I'm just kind of repeating that process for you. But in practice, you could just graph it on your calculator and look at the picture and do the same thing we did in the previous example. Troy. Yes. All right. What do you guys think here? This is a lot today, right? Yeah. We're going to stop because we're basically out of time, so we won't be able to talk about mixing this stuff all together and generating a graph yet today. So I'm going to assign problems 1 through 12 for the problem set. And I want to mention that for the virtual day coming up, that your assignment is going to, I didn't want to grab this thing. I want to grab this thing. Your assignment I'm going to have is a surprise, a Delta Math assignment. I know you're shocked by this, right? And let me take a moment and show you what you're going to be doing. So your Delta Math assignment is going to be like finding these parts, just like we did today in class. The only one that you might not feel comfortable doing yet is the graphing rational functions one. But if you look at it, what you're doing is like, you're just basically putting these things in. And, you're just kind of like one at a timing it and building the graph that way. You know what I'm saying, guys? So you'd be like, I'll put a vertical asymptote here. And then maybe I have a horizontal asymptote there. And I have like an x-intercept there. Oh. And maybe I have like a y-intercept there. And maybe I don't have any hole and I hit plot and it makes something for me. I just have to like match up after I've solved these things, just kind of put them in the graph and then hit plot and it connects everything together for you. Notice that this is obviously not right because it's not passing through my y-intercept. But that's the idea. Okay, so again, like this should be still doable. You just have to play around with it a little bit. You guys feel okay? on what to expect. So that's your virtual day assignment. It's just going to be to work on that. And I think it's available to you already if you wanted to start. So like whatever, today, tomorrow's Thursday, Friday, Saturday, Sunday, whenever you feel like doing it. And that'll be it for me.